All right, it says if a ray bisects an angle of a triangle. So that's what we've got going on here with ray CD. Okay, you see that these two angles here are congruent, so CD must be a bisector. Then it divides the opposite side, which would be this side down here, into segments that are proportional to the other two sides. Okay, so this ray, CD, is going to divide that side into two segments that are proportional to that segment and to that segment. Okay. The way we're going to start, when it says that they are proportional, it doesn't tell you directly the order of comparison. Okay. Or it's maybe not as obvious. So when it says proportional to the other two sides, so you take AD and DB, however you want to divide them. I divide them AD over DB. Okay. If you remember from pretty much everything we've done so far in this chapter, if I'm going to write a proportion, then there needs to be a common theme in regards to my numerators. And I always go with the relationship that they are always from the same shape. So if I'm looking at these two sides that I put stars on, which one comes from the same triangle that AD is in? It would have to be AC, right? Does that make sense? So basically what happens when we do this, we create these two triangles. That one there. Oh. And that one there. Okay. I'm going to look at AD compared to DB. Okay. And then AC compared to BC. And what happens when I do that is that the parts on top came from the blue triangle, and the parts on the bottom came from the green triangle. Now, that's the way I teach it. That's the way our textbook wants us to learn it. But some people are going to say, we know we're allowed to interchange those two things, right? So they're going to write AD over AC equals DB over BC, which is fine. All that does then is now the link between similar or same shapes is vertical here. AD and AC are the two sides of that triangle. And then DB and BC are the sides of that green triangle. Does that kind of make sense? So you could do it either way. It doesn't matter. Okay? When I do them together with you, I'm probably going to use, I know I'm going to use that one that I have printed up there. Okay? That, this larger one, okay? But this, there's nothing wrong with this. And then I always get the question, I don't do it that way, Mr. Fay, but I get the same answer. Is it okay? Well, it's probably okay because you're doing it this way, which is just interchanging the means of this. No matter what I ever give you, no matter what proportion I ever come across, you can interchange the means and get a true proportion. It might not be the exact same proportion, but you'll get a true proportion, which will yield the same results, okay? We saw yesterday, if you watched the video in its entirety, I talked about right here, the proof of this, okay? The idea that if I add the denominator to the top and the denominator to the top, basically adding 1 to both sides of the proportion, I can do that, okay? You can do a similar thing down here if you wanted to. Okay, if I want to add AC to the top and bottom here and add BC to the top and bottom here, I can. That's fine. Doesn't make a whole lot of sense to do that, but you can. Okay, so there's a lot of things you can manipulate your proportions as long as you abide by these rules that we talked about in chapter or section 7.1. Come up here to 7.1. These here, okay? This says you can find the reciprocal. This here says you can interchange the means. This one here is saying you can add the denominator to the numerator, okay, which is effectively adding 1 to both sides. If you do any of those three things to any stated proportion ever, you will yield a different but yet true proportion. Does that make sense? Okay. So if I ever do something in class that's different than what you're doing, and you want to know, is it okay what you're doing? Try to decipher. If you took yours and found the reciprocal or interchanged the means or added the denominator to the numerator and then ended up with what I had, then absolutely what you did was fine. So you get the questions like this. The only thing here you have to do is pay attention to is if I want to look at the angle bisector. So this is the angle bisector. Okay, so that's going to divide this side down here. Okay, so I'm going to compare the dotted blue to the solid blue. Does that make sense? Okay. Now, they're not always going to directly give me all those things right away. I might have to do a little bit of work. So if this is x, what would this distance here be? -40 x, right? Okay. So that's what I'm going to compare. I'm going to compare x to 40 minus x. Okay. And now because x was in this triangle here, I'm going to try to keep my numerators from the same triangle. So what number should go here? I'm going to put 27 there and 45 there. These two came from the same triangle, right? Does that make sense? Okay, it came from the triangle on the left, so that's the common theme in the numerator. 40 minus x and 45, they came from the triangle on the right. That's the common feature there. Can we cross multiply these things? Okay. So 45x equals 27 times 40 minus x. I don't want to grab my calculator. Let's do some thoughtful algebra here. What are factors of 45? 5 and 9, right? Okay. Now we could break that down to like 5 and 3 and 3, but I'm just going to go 5 and 9. Do you see a factor of 9 in that 27? Do you see a factor of 5 in that 40? Okay, so this is what I'm going to do. I'm going to write this as 45x equals 27 times 40 minus 27x. Is that okay? So I distributed this 27, but I didn't really multiply the 27 and 40 together because I don't want to do that, right? Maybe I don't have my calculator. Maybe I don't want to grab it. If I divide everything by 45, okay, or actually, I got to add 27 first, right? So this might not be the best thing to do then. So add 27. What's 45 plus 27? 72. All right, that's not bad. Still okay. What are numbers that do you see when you see 72? What are the factors of 72 that you see right away? 9 and 8. Do you see a 9 and 27? Do you see an 8 and 40? Okay, so I'm going to divide it here by 72. Come over here and divide by 72. So leave me x on the left. Okay, but this 72 on the bottom, I'm going to write as 9 times 8. The 9 will cancel there, leaving me a 3 in the 27, right? The 8 will cancel here, leaving me a 5 there. So it's 3 times 5. 15. Okay, and I never, if we can do things like that, and that's part of, you guys, I don't know if you guys, were you guys part of the whole, like, initiative to, like, Common Core math and that kind of stuff when you're in, like, 3rd and 4th grade? Yeah. Where you take homework home and mom and dad didn't have a clue how to do it, but it was 3rd and 4th grade math? Okay. That whole initiative was intended for you to be able to do stuff like that right there. If the state would have laid out, and it's not even the state because Common Core is federal, it's nationwide. If they would have kind of laid out that for parents and teachers at the onset, say, hey, this is the reason we're changing the way we do things instead of rote memorization, which is the way I learn things. like multiplication tables and that kind of thing, and learning essentially like division algorithms and a lot of memorization. They're trying to get you to get away from memorization and learn the facts, but teachers weren't instructed on how to do that real well. Parents obviously have never seen an instruction, and it didn't get laid out very well. But that if they would have explained to maybe parents, this is the end result, the end reason for teaching things that way, it would have made maybe more sense to parents and why we were doing it. Does that make sense? Okay, now if you don't want to do that algebra that way, that's fine. Grab your calculator and plug things in. But I think if you don't have a calculator, if you want to do things a little bit more efficiently, you can do it. And if you force yourself to do it this way, initially you might be slower, but eventually you're going to be very, very quick, much quicker than somebody that's grabbing their calculator, because you're going to see these factors easily in your mind, which will make you better at other aspects of algebra as well. This one's pretty direct. Setting up my proportion. Okay, what do you want to write in this first ratio? We've got some options, but what do you guys want to write here? X over 24? That's fine. Okay. Now, it's not the way that the theorem was presented, but if you go X over 24, I want to follow a similar pattern in the second proportion or second ratio. So 12 over 18. Okay, if I follow those similar patterns, we should be okay. Now, if we interchange the means, that presents the same thing that the theorem said. The theorem said once you have the angle bisector, if you compare the parts of the segment that the angle bisector intersects, those should be proportional to the other two sides. So X over 12 compares to 24 over 18. Either one of these is fine. Okay? Because when I cross multiply, do I still get 18x and 24 times 12? Now, I'm not going to multiply the 24 and 12 because in 18, what are some factors you see in 18? 6 and 3? Okay, do you see a 6 in this 24? Do you see a 3 in the 12? So that 6 is going to cancel there, leaving me a 4. That 3 is going to cancel there, leaving me a 4. So it gives me 16. All right? Do this one on your own. All right, so the most probably conventional way that you would have found x here is to write 5/8 equals x over x plus 6, or 5 over x equals 8 over x plus 6, right? Cross multiply, get 8x equals 5x plus 30. 3x will equal 30. X will be 10, right? I wrote these. I'm not going to go through and solve these with you because some of them get pretty nasty. But these are additional things that would also work. Okay? But if you look at them, all I did was I started with this one, and I took the denominator and I added it to the numerator. I got this one here. Took x and added it to the top. I got 5 plus x over x, right? Okay? Because if you think about what I did by doing that, if I separate that fraction, it's 5 over x plus x over x. Do you guys agree with that? Okay, that's kind of undoing a common denominator there. Usually we start with this and we'll rewrite it as 5 plus x over x, but you can undo it as well. And this one would be, 8. I can write it as 8 over x plus 6 plus then x plus 6 over x plus 6. Is that adding 1 and is that adding 1? Does that make sense to everybody? So if you did it, that's fine, because if I had an equation that was true, we knew 5 over x it was true to be equaling 8 over x plus 6 from there. Add 1 to both sides. You kept things balanced, correct? Does that make sense? Okay. So if you did this, I think maybe we should have a discussion and talk about maybe an easier way for you to do it, but it is 100% okay. Does that make sense? These two are more logical, and I talk about that for my hope is that nobody did that. My hope is that nobody ever does that. But in the past, I would always get questions through 12, 13 years of teaching this. Mr. Fay, you showed a proportion that I don't have on my paper, but we got to the same answer. So I got a different way. I beat mathematics. I have a different way than you do. Okay? And then we analyzed their way and realized that it is just because they either interchanged the means, they found reciprocals, or they added the denominator to the numerator. Okay? Or they did multiple of those things. That makes sense? Maybe they found the reciprocal, interchanged the means, and then added the bottom to the top. That will generate something completely new, but still works. Does that make sense? Okay. So people always argue like they got something, and this goes through all of mathematics. Did it differently than you did. Well, did you or did you not? Because if we really investigate it, chances are, based on our properties and abiding by our rules, you probably did it the exact same way. Okay. Do we think we can do some questions like that? They're not going to get any more difficult than those there. Watching yesterday's stuff, do you guys have any questions over these? Again, with these, there are so many different ways to come back up here. These are all relationships that can exist when we take 3 or more parallel lines and cut them with transversals. Okay. A lot of these rules generate because if I were to continue these parallel lines or these transversals, I eventually start to get a triangle. And we can go through triangle similarities to basically develop and generate these things. Okay? But we can say AB compares to BC just like DE compares to EF. Okay? So that compared to that just like this one compares to that one. Okay? You can also say that AB, this one here, compares to that, just like this one here compares to that one. Does that make sense? You see how we're trying to follow the same similar pattern as what I choose on the left-hand side as what I choose on the right-hand side. Okay? And then the last one would be BC compares to AC, just like EF compares to DF. Okay? That's by looking at just individual transversals and making a ratio of the individual transversals. But I always get people to say this. I didn't do it that way, Mr. Fay. I said AB compares to DE. They said, I'm going to compare this one to that one. AB compared to DC. Yeah, we jump now from one transversal to the next in the same ratio. And then they say, well, then I'm going to compare BC to EF. BC to EF. And they say, I did it completely different than you. But if you interchange those means right there, does that give me that right there? So it's not different, right? Does that kind of make sense? All right. I think these ones in yellow are the ones that are most basic, most obvious, safest to use, but you've got options. Okay? If you know your rules about generating equivalent proportions, provided that your initial proportion is true. Okay. You guys have any questions on anything over the stuff that I gave you online, worksheet, anything from, say it again? 7-4 worksheet. Which ones do you want to talk about? We got time. We get out of here. We got 20 minutes, so we can talk about any number of these. 11 through 16. Number 11. So I believe that these other ones down here, especially the last like 4, those are probably the most difficult. Let's at least, I'll at least set up the algebra for you with number 11. Remember, if we're going from the right angle to the hypotenuse, this altitude here is a geometric mean between the two segments that are created on that hypotenuse. So we should have that equation for solving for x. This leg here is also a geometric mean because it's our other altitude. So I'll put y there. Now it's between the entire hypotenuse and then part of the hypotenuse that is touching that leg. So this would be 8. So that's 16, and then that 8. Then if I want to find z, that is our other leg. So it is the geometric mean between the entire hypotenuse and the part of the hypotenuse touching that leg. What's that tell you about y and z? They're equal. So what kind of triangle is this? It is an isosceles right triangle. So what's going to find out is that, so that's 16. You get 8 radical 2 for y and z, I believe. Chapter 8 will actually allow us to do this problem here a little bit quicker than what we have with these tools. Number 12. I think a lot of people get hung up on questions like 12 because we've been, and a lot of the questions that I gave you and what Math Excel gives you, it programs you to look at that segment, and that segment. But those segments in the questions that I've given you are predominantly X, Y, and Z, right? Here they're not, okay? Even the purple one's not even defined. So what we want to do here is I'm going to look at the 9. The 9 is a leg, and it should be a geometric mean. Now, it's a geometric mean between the hypotenuse. So what is the hypotenuse here? X. Be x plus y, wouldn't it? Okay, so I can write it as x plus y. But what's a better option? 15. Okay. Then, so it's a geometric mean between the hypotenuse and the part of the hypotenuse that is touching the 9. So it'd be x, right? Okay, so here's my question. If you know, so that's going to be what? 15x equals 81. X equals 81 15ths. There's a 3 in both those, so it gives me 27 fifths. I'm going to leave it as that. Okay. Now, because it ends in a 5, or it's a division by 5, so like if you change this to a decimal, it'd be like 0.2, 0.4, 0.6, 0.8, something like that. Do I know what y is automatically now? Well, you told me x plus y was 15 a minute ago, didn't you? Okay, so 15 minus 27 fifths. Okay, so that's 75 fifths minus 27 fifths, so that would be what, 48 fifths. If this was 25 fifths, it'd be 50 fifths. So I think that's right. And now, if I want to find z, z is my altitude. It goes there and there. Between x, we just said x was 27 fifths, right? And y We just said y was 48/5. Now the algebra there, I think, can probably be kind of messy, solving for z. So we get z squared is equal to 48/5 times 27/5, right? What's 5 times 5? 25. Now I'm going to write the bottom as that. I'm going to leave the top alone. If I take my calculator, because we're going to simplify, we're going to take square roots, right? Square root. That's going to yield z equals whatever square root of 48 times 27 is. What's square root of 25, though? 5. Okay? But if I multiply the top out and got the number, so let's go ahead and do it real quick. I'll do it. 48 times 27. Change that top to 1296. Okay? You are then going to start factoring 1296. And what will you eventually get to? 48 and 27, right? That kind of makes sense? So you see how grabbing my calculator and multiplying those out might be kind of a waste of my time. Okay? Unless, does anybody know what kind of number 1296 is? It's a perfect square. Do you know what the square root of 1296 is? So this is common knowledge that is not all that common, right? Does that kind of make sense? So this gives me 1296. Had to have my calculator to do that. Had to have my calculator to realize that that's 36 times 36. But if I'm taking a square root here, and I say, okay, well, 48, we've done square root of 48 and square root of 27. So 27 is 9 times 3, right? 48, is that 16 times 3? Does that make sense to everybody? What's the square root of 16? 4. What's the square root of 9? 3. That 3 times 3 is a 9, right? What's the square root of that 9? 3. What's 4 times 3 times 3? 36. So that's what this top turns into, 36/5, and that's our z value. If we look at 16, not 16, you want to do 13 or? Is 13 one we want to do? Look at that z. Shouldn't that be the geometric mean between that distance and that distance, right? One of those distances is 2. What's this distance here going to be? How do I identify? That yellow distance would be x minus 2. Can you solve that right away for x or z? It's a problem, right? Don't erase it. Just go on to another relationship. We'll look at this 6 right here. 6 is the leg, so it's a geometric mean between that distance there, which is x, and a portion of x that's touching the leg of 6. So 2. Does that let you solve for x? 2x equals 36, so x will be 18, right? Now, if x is 18, does that tell me what I can do up here? 16 should go there, right? Zoomed in too far. Okay, so if x is 18, now I can go up here and say z squared equals 2 times 16. Square root that. Square root of 2 is just square root of 2. What's square root of 16? 4. So we got 4 radical 2. And then if I want to find z, all right, I did z, y. I'll find y. That's the geometric mean between x which we already know x, we found that to be 18. And now the part of that 18 that is touching y, well, that part of the hypotenuse that's touching y would be 16, wouldn't it? So now I get y squared equals 18 times 16. You can grab your calculator, multiply 18 times 16. I think that's foolish. I'm just going to take square root right away. Okay, what's 16 change to? What's radical 16 the same as? 4. Now what perfect square divides divides 18? 9, right? So if that's 9, this would be 2. Take radical 9, that gives me 3. Times radical 2 times this 4 gives me 12 radical 2. So that's my y value. Okay? But like I say, you get that 12 radical 2 a different way. If you go 18 times 16, 18 times 16, 288, and say, well, that's 2 and 144, that's 2 and 72, that's 2 and 36, that's 2 and 18, that's 2 and 9, that's 3 and 3, and say, there's a group of 2s, there's a second group of 2s, so 2 times 2 comes out as that 4 right there. Does that make sense? Okay. This group of 3s is that 3 right there. And then this green 2 is that 2 that's left underneath. So you can do it this way. I just think that, and this is all of mathematics, the way I do a lot of the algebra that I do is because we learn properties and relationships so that we can circumvent math. Okay? People think math is just calculations, right? That is actually a very small portion of mathematics. It's learning the relationships and the structures that allow us to actually circumvent or go around calculations like this. Okay? So that's why I do things like this. Set these other ones up. Let's go 14 would be, so if y is the geometric mean, we're going to go between x plus root 2 and x. Okay, that's kind of a nasty equation. You're not going to be able to solve for either x or y. So I'm going to look at z then. And that should be the geometric mean between x and radical 2. Still a nasty equation, 2 variables. So we're going to look at the 2. Should be the geometric mean between x plus root 2 and root 2. That one only has one variable, right? So let's cross multiply. What's 2 times 2? 4. Now when I do this, I need to distribute. And this radical 2 is just it's just a coefficient. It's 1.4 something. So I take 1.4 times x. It should give me 1.4x. But we don't write it as 1.4, we write it as radical 2. Does that make sense? And then I distribute radical 2 times radical 2. Well, that gives me radical 4, which is just 2, correct? So I distribute that to that. This is what I get. Subtract 2 from both sides. Okay. Now, this is my coefficient. This is saying like 1.4x. If I had it written as 1.4x equals 2, what would you divide both sides by? You divide both sides by 1.4, wouldn't you? This is representing that 1.4. So what am I dividing both sides by here? Radical 2. Does that make sense? So then I have 2 over root 2 equaling my x value. I don't know if we've talked about it, but we don't like radicals in the bottom. So we rationalize it. We write it as 2 radical 2 over 2. After 2. And what's that going to happen with these 2's outside here then? They cancel. Leaves me just radical 2. That's my x value. So So we have 2 over radical 2. That was our answer, right? And that's fine. But we don't like it just, and the reason for this is because of future algebra that we might do. And we can see it here in this problem. That if I were to, so this is the x value that we found. If I plug that x value into this problem, it makes this problem up here a lot more difficult. If I plug that x value in right here, it makes this problem a lot more difficult to find z. But if I simplify this, and the simplification process is to get rid of this radical in the bottom. We call it rationalizing the denominator. What I'm going to do is I'm going to multiply by whatever that denominator is, or whatever the radical in the denominator is. If I multiply by that radical 2 or radical 2, what is that the same thing as multiplying by? 1. Okay? So I'm not going to change what this blue number is, right? I'll change the way it looks, but I don't change the blue number. Radical 2 times radical 2 is radical 4, which just changes to 2, right? When we do this, we can rewrite this as 2 over 2 times radical 2 over 1. What's 2 over 2 the same as? 1. So what's 1 times radical 2 over 1? Just radical 2, right? So now radical 2 is a better answer than that. It's better format, because now future algebra says when I put radical 2 here and radical 2 here, it makes solving for y a little bit easier than if this was radical 2, or sorry, if this was 2 over radical 2. So now, what's radical 2 plus radical 2? It's 2 radical 2s. If I cross multiply, then I get y squared equals 2. Radical 2 times radical 2 is radical 4, which is just 2. So you get y squared is equal to 4, so what's y? 2. Where if I would have left that as the fraction of 2 over radical 2, we're probably doing all the math and then some that we did down here. Same thing can be done then for that z. This is radical 2. So radical 2 times radical 2 is 2. So I get z squared is equal to 2. So z is equal to radical 2. So again, this ends up being we'll talk about this type of image tomorrow, or not tomorrow, I guess next chapter. But this is a segment of 2. This is 2 radical 2. Because of this information on these sides, I can guarantee to you that that angle right there is 45 degrees. And you have absolutely no knowledge other than these distances to tell you that. Okay? We'll talk about that, and that's what the next chapter is about, is seeing images like this and knowing if that's 2, that's 2. This has got to be 2 radical 2. We'll stop there. Tomorrow, we should have time tomorrow if we want to go over 15 and 16 as well. Plan on it not being, but don't leave your notes at home. I will. Are radicals the thing that throw us off that algebra? I will attempt, because I do want to test you on your radical knowledge, but I will attempt to make the questions so that radicals are not a reason why you do poorly on the test. Does that make sense? If you do poorly on it, not saying I'm going to nix them completely, but I will alleviate some of that for you. Yes. Yeah. All right, so the way I would compare these is I would say 4x compares to 5x. and then 6x plus 4 compares to 8x minus 15. Does that make sense? Now, there's other things you can do. You could say, 4x compares to 9x. So that's the top one compared to the whole thing. And 6x plus 4 compares to this whole thing, which would be 14x minus 9. Okay. Now that makes coefficients much bigger, right? Now there may be applications on why, depending on how these coefficients and these other parts relate to each other, this might eventually in some problems be a better route than what this was. But regardless, if I cross multiply, okay, I get 30x squared here plus 20x equals, then multiply here, I get 32x squared and then negative 60x. So right off the bat, I notice I've got x squared, so I got to get everything equal to 0. Okay? So I'm going to move this 30x squared to the right-hand side. So it'll give me 2x squared. And I'll move this 20 over there as well, so give me minus 80x. That should equal 0. Does that make sense? Okay. Now, if I have an equation, this is a quadratic equation, but there's no c term. So every quadratic equation is ax squared plus bx plus c. But right now we don't have that. If it was this, I would factor using like two numbers that multiply together to give me c and add to give me b. But because that c term is gone, we're going to use the technique of looking for a GCF, a greatest common factor. What will divide both of these? 2x. 2x is in both those terms. When I factor out a 2x out of this first term, what am I left with? X. And what are you left with here? Minus 40. So this is all equal to 0, right? So now you have two things multiplying together to give you 0. So that means that one of them is 0 or the other one is 0. This one will give me x to be 0 and this one will give me x to be 40. Okay? Now, if x was 0, what would that tell you about these three lines, at least on this transversal? If x was 0. Say again? Say again? They would not be parallel. It would actually be the antithesis of parallel. Anti-parallel, meaning that they would intersect, right? If x was 0, this distance would be 0 here, right? This distance would be 0, right? Now this distance would be, now if this is negative, so that distance would not exist. That would be 4. But if these were both positive numbers right there, if that was like a positive 15, these being both 0 would mean that all three of these points right there would be that point right there. Does that kind of make sense? But that's why 0 is not an answer and why 40 is the only answer. It's because these distances would be either 0 or negative, and then that image doesn't exist anymore. Depending on the numbers you get, because you see here it says type an integer or a simplified fraction, use a common and separate answers as needed. Some of you might get, like, however your numbers relate to one another, you might get two answers down here that work. Maybe you get a 10 and a 40. So you would put 10 in comma 40. Maybe they both work. Just depends on how your values are provided. Have a great rest of the day.